Welcome to this explainer. Today, we are unpacking a seriously exciting and highly consequential new paper from MIT researcher Lei Huang. We're going to tackle a massive systemic problem in network science. Mainly, how in the world do you map invisible influence networks without having to just guess the exact rules of how they work? It's a fascinating puzzle, so let's jump right in. Now, this right here is literally the ultimate detective question. Think about it. Whether you're a marketer trying to track exactly how a viral product trend took off, an epidemiologist tracing the spread of a disease, or maybe a financial analyst trying to figure out how localized banking distress snowballed into a systemic market crash, you are looking for the exact same thing. You want to know who infected or influenced whom. But here's the really frustrating reality. In practice, the true network is almost never observed directly. We simply don't see the actual microscopic moment of persuasion.
Okay, so here's our roadmap for today. We'll look at the hidden influence network, the problem with guessing, and then introduce CascadeNet. After that, we'll talk about cleaning up the data, put it all to the real-world test, and wrap up with why this actually matters for you.
All right, let's kick things off with Section 1, the hidden influence network. So, because we rarely see who actually influenced whom in real time, we have to rely on the clues left behind. And in this field, those clues are called cascades. These cascades are basically the visible footprints of our invisible culprit. Imagine you're observing a group of people over time. You see the sequence of events, like when a person buys a product, when a patient tests positive, or when a bank defaults. Our entire goal here is to take this really thin record, these observed cascades, and reverse engineer them to recover the underlying hidden structure of influence. Which brings us to Section 2, the problem with guessing. To trace these footprints, older detective methods relied on a technique that frankly had a massive, fatal flaw. These classical methods required you to assume a very specific mathematical role for how influence propagates. You basically had to force a specific theory of the crime right from the start. But let's be real, real-world reality is messy. Influence is complex and driven by multiple factors. So if your initial guess about how things spread is even slightly wrong, the accuracy of your entire mapped network just completely falls apart. You end up with a highly detailed map of a network that literally does not exist. And that leads us perfectly into Section 3. Enter CascadeNet. To completely avoid this trap of having to guess, MIT researcher Lei Huang developed a brilliant new machine learning framework called CascadeNet. Instead of forcing a rigid model onto the data, CascadeNet targets something called the Jacobian. Now, mathematically speaking, that's a matrix of partial derivatives. But practically, think of it as a superpowered mathematical magnifying glass. It zooms right in on the marginal influence between any two specific actors. It essentially asks, given the current state of the world, exactly how does a tiny, tiny change in agent J's state affect agent I's outcome tomorrow? This is a total game changer because it lets CascadeNet measure direct influence without making any rigid assumptions about how that influence travels. To actually crack the case, CascadeNet uses 3 surprisingly simple steps. First, it uses flexible machine learning to estimate how events transition over time. Second, it differentiates that function by taking that Jacobian we just talked about to map the hidden network. And third, it applies a really crucial statistical correction called Riesz debiasing. So we let the algorithm flexibly learn the patterns, zoom in to find the influence, and then scrub the final result to ensure it's incredibly accurate. Speaking of scrubbing the results, let's look at Section 4, cleaning up the data. You're probably wondering, wait, why do we even need that third step? What are we debiasing? Well, there is a major catch when you use standard machine learning for this kind of forensic network science. Standard ML estimators use regularization, like L1 or L2 penalties, to control variance and stop the model from overfitting. But because it automatically controls for variance by shrinking the estimated parameters towards 0, it unintentionally introduces statistical bias. It's literally hiding the exact influence signals we are trying so hard to detect. If the Jacobian is our magnifying glass, this regularization is basically a thick, greasy smudge right on the lens. If you ignore it, you will systematically underestimate the strength of those network connections. So how do we wipe off the smudge? By applying a complex mathematical correction called Neyman-orthogonal debiasing via the Riesz representer. It sounds super intimidating, but intuitively, it just converts errors in the prediction into corrections for the derivative. It wipes the lens clean using observable prediction residuals. And the results? Absolutely wild. In a controlled simulation with a known mathematical ground truth, applying the specific Riesz correction achieved a 1.70 times error reduction compared to the naive machine learning approach. It literally restores the crucial network signal that regular ML would have just completely destroyed.
All right, let's get into the evidence in Section 5, putting it to the test. Sure, all of this sounds mathematically elegant on paper, but does it actually work in practice? Well, check out this chart. We are looking at performance across 9 completely different simulated universes, everything from simple cascade models to highly complex nonlinear processes. Look at the orange bars representing CascadeNet. It is absolutely dominating the classical baseline methods, which are in gray. An older method might do okay on the one specific dataset it was built for, but then completely crash and burn on the others. CascadeNet's flexible approach consistently dominates across the board. And we see the exact same story in these precision recall curves for network edge detection. Visually, the sheer dominance of the orange line over the gray lines proves that CascadeNet maintains substantially higher precision. Whether the trend acts like a complex social contagion requiring multiple exposures or just a standard epidemic, CascadeNet consistently recovers the true network topology. Meanwhile, those rigid baseline models, they just fall apart.
But here is the ultimate real-world test. The researchers took this and applied it to actual COVID-19 case counts across 52 Spanish provinces. The goal was to recover the transmission network using only daily infection data and then validate it against actual cell phone traveler mobility data. Look at the Pearson R column on the right. That measures the correlation with real mobility flows. The old baseline methods, they scored negative or basically zero. They completely failed to find meaningful transmission pathways. CascadeNet, however, was the only method that successfully reconstructed transmission networks that aligned positively and significantly with actual human movement. It extracted a real, meaningful signal from incredibly noisy epidemic data. And get this, it did it without ever even seeing the mobility data during training. Finally, let's wrap things up with Section 6, why this matters.
Let's take a step back because the real-world impact of mapping these unseen connections is massive. A misjudged connection in a network can mean a totally wasted promotional budget, a missed disease superspreader, or a financial contagion risk that gets completely overlooked until it's too late. Because CascadeNet doesn't require you to guess how things spread, and because it mathematically debiases the data, it gives you something incredibly rare in this field: actual, valid, statistical confidence intervals. Whether you're a marketing manager planning a huge campaign or a public health authority allocating resources, CascadeNet gives you the rock-solid mathematical confidence that an influence edge is statistically real and not just an artifact of noise or a bad guess. So now that we finally have the ultimate tool to trace these invisible threads without relying on rigid assumptions, I've got to ask you to think about your own field. Whether it's the hidden flow of information in your company, the unseen drivers of customer churn, or hidden vulnerabilities in your supply chain, what hidden influence networks are just waiting to be uncovered in your data? Thanks so much for joining me on this explainer, and keep questioning the unseen.